Hello everybody, in this video we're going to develop the equations of motion for an object with constant acceleration. If you remember from the last video, acceleration is just the rate of change in velocity. So any change in velocity is an acceleration. Remember that acceleration is a vector quantity, so the direction matters. If the acceleration and velocity are in the same direction, the object is speeding up, and if the acceleration and velocity are in opposite directions, the object is slowing down. The SI unit, the base SI unit for acceleration is just meter per second squared. Okay? And these equations of motion are typically referred to as the kinematic equations. They are the first three equations on our equation sheet. And we're going to develop these equations by starting with two simple definitions. And it's important because anytime we solve a problem in AP Physics, we have three options to start. We can go directly to the equation sheet, and we have to use something that's on the equation sheet, or we can use a law or a definition. And those are the only three places we can start. There's a bit of a danger to finding resources online. If you find videos to get some help with physics, or if you have a tutor, you just want to be careful that those resources are not giving you the developed equation specific to one problem. Instead, what we want to do is we want to learn the equations that are on the equation sheet and be able to manipulate them ourselves. Because as I said, for any free response, we have to start there, either with a definition, a law, or one of the equations on the equation sheet. Okay? So I'm going to start with two definitions. The first being average acceleration is change in velocity over time. And for an object with a constant acceleration, I would say then that I can probably just drop the idea of an average, because if the acceleration is staying the same, then it's always whatever value. So I'm going to just drop that line and call it acceleration. And acceleration is change in velocity, which we know would be final minus initial. So final minus initial over time. And the last thing I'm going to do here is go ahead and rearrange, so getting time off the bottom. So by multiplying both sides by t, I can see that acceleration times time is equal to v final minus v initial. The last thing that our equation sheet is going to do is just move that v initial over to the other side so that you've solved for just v final. So that would look like v final is equal to v initial plus AT. And that's what's referred to as the first kinematic equation. So it describes how we could find the final velocity if we know the acceleration, time, and initial velocity. Okay? I'm also going to use the definition of average velocity. Average velocity is displacement over time. Now, typically, average velocity, your velocity could be changing. And if your velocity is reaching different values for different amounts of time, then this is a pretty complex problem. But we can always get the average by doing displacement over time. However, as long as the acceleration is constant, it means that every value of your velocity is reached for just an instant. And if every value of velocity is reached for the same amount of time, then we can actually do this average as an arithmetic mean, or just finding a regular average between two values. So I can, only for constant acceleration, I can write the average velocity as 1/2 times v initial plus v final. Right? If you want to find your average score between two tests, you would add them up and divide by 2. So that's what we're doing here, but just keep in mind, and you will see this in some resources as an equation, just keep in mind that this average only works because we have constant acceleration. So my average velocity is 1/2 v initial plus v final, but we know average velocity can always be found by doing displacement over time. So I'm going to go ahead and move t to the other side. So I have 1/2 times v initial plus v final times t is equal to the displacement. And the last thing I'm going to do is I'm going to take the first kinematic equation, v initial plus AT, and I'm going to substitute it in to this definition right here. So where I see v final, I'm going to replace it with v initial plus AT. So this looks like 1/2 times v initial plus v final, but I'm replacing v final with v initial plus AT. And then the rest of that equation is t equals delta x. Okay, I can now combine like terms. I see v naught plus v naught, which would be 2 v naught, and then there's this leftover at, and then the t outside of the parentheses is equal to displacement. Now, when I see a number next to a parentheses, I'm compelled to distribute. So I'm going to go ahead and distribute that 1/2 into the parentheses, and I'm also going to distribute the t as well. So when I distribute the 1/2, I get v naught plus 1/2 at, and then I'll go ahead and distribute the t as well. So when I distribute t like this, I get v initial t plus 1/2 at squared is equal to the displacement. And this is referred to as the second kinematic equation. Now, to get the third kinematic equation, the algebra is a little bit intense, and I don't know, if you want to see that video, I can, but it's probably not worth your time to see that. What happens to get the third kinematic equation is very simple. The third kinematic equation is independent of time. So how do we get rid of time? We could, in the first kinematic equation, solve for t, and then plug it in for time in the second kinematic equation. And that's going to eliminate t. And the result that we get, the third kinematic equation, is just v final squared is equal to the initial velocity squared plus 2a delta x, or 2a displacement. And that's our 3 kinematic equations. Okay? Now we can use those to solve different problems. What I like to do for each of these problems is to write down the 5 kinematic variables: acceleration, displacement, v initial, v final, and time. Now with those kinematic equations, as long as I know 3 of the kinematic variables, I can always find the other 2. That's just the mathematical minimum. You need to know at least 3 of them to find the other 2. And in this particular problem, it says a car is traveling on a straight road. It increases its speed from 10 to 25 meters per second in 5 seconds, assuming constant acceleration. So that allows me to use the kinematic equations. Now, the initial velocity is 10, because that's what it's starting with. The final velocity is 25. And it says it takes 5 seconds in order for this increase. So we have a time of 5 seconds. Now I could use any of those kinematic equations to find either displacement or acceleration, but in this particular problem, they're asking me for the acceleration. So I'll look at those 3 kinematic equations and I'll say, which kinematic equation has acceleration, initial velocity, final velocity, and time? If it has all 4 of those, that's the one I'm going to use to rearrange to find acceleration. And if I look at the first kinematic equation, it says v final equals v initial plus at. Now I want to find the acceleration, so I'm going to rearrange this equation for a. And I'm going to do this before I put numbers in. And the important reason behind that is sometimes things are going to cancel out. Things that you might not have information about can drop out as long as you do the arithmetic with these letters. So I'm going to go ahead and try to solve for acceleration by subtracting v initial and then by dividing by time to get a by itself. Now I have each of these values, so I can plug in my final velocity of 25, my initial velocity of 10, and my time of 5 seconds. And that should be 15 divided by 5, or 3 meter per second squared. Okay, so that's using the first kinematic equation and rearranging to find a. Let's try another one, a different one. So a car starts from rest and accelerates at a rate of plus 3 meters per second squared for 5 seconds. Determine how far the vehicle travels. Again, I'm going to write down those 5 kinematic variables: acceleration, displacement, v initial, v final, and time. And I'm just trying to list what I know. What have I been given? We have some implied data here. It says starts from rest, which means our initial velocity is 0. It accelerates at a rate of plus 3 meters per second. So our acceleration is 3, and I see here seconds, so that must be our time of 5 seconds. Determine how far the vehicle travels. So we're looking for the displacement. I'm going to look for any kinematic equation that has acceleration, displacement, v initial, and t. As long as it has all four of those, I'll be able to rearrange to find displacement. And it looks like the second kinematic equation, which is v initial t plus 1/2 at squared, has all four of those things. So it's already rearranged for displacement, so I'm going to go ahead and plug in my values. The initial velocity is 0 times 5 seconds plus 1/2 times my acceleration, which is 3, times t squared. So I have 5 seconds squared. Well, 0 times anything is 0, so that first term goes away, and I'm just looking at 1/2 at squared. So I'm going to go ahead and put that in the calculator. For 1/2, I'll just do 0.5 times the acceleration times 5, and then I have this little squared key here. So 1/2 at squared, and I'm getting 37.5. And since it's displacement, the units would be meters. Okay, let's do one more using the third kinematic equation. Along a 100-meter drag racing strip, a car accelerates from rest at a constant rate of 0.5 meter per second squared. Determine the velocity the drag racer reaches at the end of the drag strip. Again, let's list our 5 kinematic variables: acceleration, displacement, v initial, v final, and time. 100 meters, that looks like a length here, so it's a 100-meter drag racing strip. That will be our displacement, 100 meters. Accelerates from rest. So again, we have some of that implied data. From rest means the initial velocity is 0, and our acceleration is a rate of 0.5, so 0.5 meter per second squared. Okay? Determine the velocity of the drag racer at the end. So that must be the the final velocity. So I'm looking for final velocity. I will try to find an equation that has a, displacement, v initial, and v in it, which would be the third kinematic equation, which says v squared is equal to v initial squared plus 2a delta x. And again, it's already rearranged for v squared, so that's good news. I can start to substitute my initial velocity, 0 squared plus 2 times the acceleration, 0.5, times the displacement of 100. And that's going to give me my final velocity squared. Well, that's great, but I don't want the final velocity squared. I want just the final velocity. So how do we get rid of a squared? To get rid of that squared, we're going to take the square root of both sides of the equation. So taking the square root of v squared will give me just v. And over here, since 0 squared is 0, I have just the square root of 2 times 0.5 times 100. And again, I'm going to put that in a calculator. I'll do second square root 2 times 0.5 times 100, and then close the parentheses. Okay? And the square root of 2 times 0.5 times 100 is 10, and then I'll report the correct unit for velocity. That should be meter per second. So the final velocity is 10 meter per second. Okay? Just want to take you to the equation sheet really quickly. These are the 3 kinematic equations as they appear on your equation sheet. Okay, so if we look at the equation sheet, the first page will give you a lot of your constants. You'll also have the metric prefixes and some of your common trig functions with angles. If we move on to the second page, all of Unit 1 is going to be contained right here. So we're just using those first 3 kinematic equations. You're going to notice one thing that's a little bit different here, and that's that x subscript. And what that means is that these kinematic equations, they only work in a straight line. They work in one dimension. So they're putting that x there to remind you that these are along an axis. When we get to 2- and 3-dimensional motion, remember that while our equations only work in one dimension, we will use trig in order to break down those multiple dimensions into independent one-dimensional motion. Okay, so that, again, that subscript of x is just there to remind you that these work for one dimension or straight line. So we need to do each dimension independent of each other. Okay? All right, so those are your 3 kinematic equations. Thanks for watching.